Good. So today what we are going to do is we are going to have a doubt clearing session on strain, and we are going to look into the problems, some problems of structural or statically indeterminate cases. Now, uh, I have been taking this doubt clearing session for the other 6 sections. They are already over. So from that perspective, I am telling you that I will not right now go into the reason why we calculate strains and why we need to know the deflections, because if I go into that, then it will become very difficult to complete whatever that I want to complete. Okay, so I will skip this part up, and I suggest that you take a look at the video which I had circulated, or the material from the previous sessions of doubt clearing. So that will be, I think, more beneficial. Now, we straight away will jump over to strain. So consider over here a situation where you have a bar. This bar BC has a cross-sectional area. It has a uniform cross-sectional area, and this uniform cross-sectional area is denoted by A. Under the action of, let's say that this end C is subjected to some force P. That is, I am incrementing a load from 0 until it reaches a value of P. And this load is going to act at point C. Now, what would you expect? You would expect that the end C, since we are no longer working with the rigid bodies, we are working with the deformable bodies, we would expect that the end C is no longer going to remain at its original position. Rather, it will start to show some amount of deflection. There will be some deformation in the beam, and there will be some change in position of the end C. Let this change, let this deflection or deformation be delta. Now, as I said that I am incrementing the load slowly from 0 to a certain value P, I obtain the final value of deflection to be delta. So, if P takes a value P naught, let's say I get a value delta naught. If P takes a value P1, I get the value of delta to be delta 1. In this way, I can construct what is known as the force displacement or force deflection diagram. Now this diagram, force displacement diagram, is very useful and at times very powerful also. So you see what, if you focus your attention towards this diagram, you would see that the initial stage of the force displacement diagram is linear. That is, in initial stages, force is directly proportional to delta. And the similar situation occurs in springs also, right? You take F is equal to Kx or F is equal to minus Kx. So there you see that the force is also proportional to the displacement which is being exhibited by your system. But if you keep incrementing the force, you reach some point beyond which the force displacement diagram starts to exhibit nonlinearity. When it comes to the design perspective at the stage that you are in right now, we will only limit ourselves to the situation we will only limit ourselves to the cases where the force displacement or the force deflection diagram is linear. We are only going to work with linear force displacement diagram. But despite this force displacement diagram being very powerful, it also suffers from some inherent disadvantages. For example, consider the bar shown over here on the right hand side. This bar, let it be called B dash C dash. Let this bar be made up of the same material as that of our bar shown on the left hand side. But let this bar have a cross-sectional area 2. So like in the previous case where the bar was BC and the length was L, for our case B dash C dash, the bar has a length L and it is made up of the same material, but it now has double the cross-sectional area. Experiments show experiments show that I would require a force of 2p in order to have the same amount of deflection as that of my original bar. So you see, my force displacement curve, force deflection curve is dependent upon the geometrical parameters of the specimen, which in this case is a circular bar. Okay, so take another situation. In the next situation, we have over here a bar, which I am drawing. This bar, let this be called B double dash C double dash, and let this bar be subjected to a force P. It is made up of the same material as BC. It has the same cross-sectional area as BC, but now it has a length of 2L. So you see, when I perform an experiment with this configuration, I would observe that the end C undergoes a deflection value of 2 delta. It is not undergoing a deflection value of delta, but it is undergoing a deflection value of 2 delta. So my force displacement curve in this situation is also going to be different than what I have drawn over here for my specimen BC. So in other words, despite force displacement curve being very powerful, it suffers from the limitation that it changes. The force displacement diagram changes depending upon the geometrical aspects of the parameter. But let's say when you are working as an engineer, when you are going about designing something, you should be having one single graph based on which you should be able to design. But here, as you can see, if I change the cross-sectional area, I get a different curve. If I change the length, I get a different curve, which is not very useful from a design perspective. And that is more so true because all the three bars are made up of the same material. So some ingenious researchers over the years thought, why not we try to remove the effect of the geometrical aspects and create a curve which only focuses on the material properties. In order to do that, what we usually do is, one of the quantities of interest for us would be the stress sigma n, and this stress is defined as P by A. So with this definition of stress, force per unit area, where the area is the perpendicular, basically the cross-sectional area on which the force acts along the direction in which you are considering. So this is independent of the area. So if you see in our first case, in our case BC, I have sigma is equal to P by A. In the second case, as shown in the right hand side, B dash C dash, I have sigma is equal to 2P by 2A, which is also equal to P by A. And on the third case, which is B dash C dash, I have again sigma equal to P by A. So irrespective of the area, if I plot instead of the force, I plot the quantity normal stress, then I am able to find out a quantity on the y-axis which is independent of the geometrical parameter cross-sectional area. But I have still not been able to define a way in which I can remove the effect of the length. In order to do that, I bring in the concept of strain, epsilon n. And let me define this quantity for a bar of uniform cross-section as deflection by original length. Okay, with this explanation, with this description, you can see that all the different parameters are now going to be exactly the same. The quantity epsilon for bar BC is going to be equal to delta by L, which is the change in length by original length. The quantity epsilon for bar B dash C dash is also going to be equal to delta by L. And the quantity epsilon for a bar which is B double dash C double dash, that is the bar which has double the length, is going to be equal to 2 delta by 2L, which is also equal to delta by L. So now, if I plot on my y-axis, as I had said, instead of force, if I plot the stress sigma n, and on the x-axis, if I plot the strain epsilon n, where epsilon n is defined as a quantity that I have just described, I end up with the curve which is known as the stress strain diagram. And this stress strain diagram does not include the geometrical aspects. It is only the property of a material. Okay, so keep that in mind. But there is another interesting thing which is happening over here. The bar, if you look at this bar over here, this bar or this bar or the bar BC is subjected to an axial force. All the three bars are subjected to axial force. As a result, in other words, my line of action of the force, all the forces intersect with the axis of the member itself. So the line of action of the force and there is no difference between the line of action of the force and the axis of the member under consideration. If I apply the load in this manner, that load is known as an axial force. And under the action of axial force, the member is getting elongated along the axial direction. I should not say only, because if you change your cross-sectional, if you look at a different cross-sectional plane, you would definitely find some kind of a shear strain there. But if you focus your attention on a cross-section which is going to be perpendicular to the axis of the member, and on that cross section you are only going to have normal stress sigma n. Keep that in picture. As a result of that, you are having normal strains also. So such kind of an situation where you get extension along one of the direction, where the load is only acting along that direction and the load is axial, is known as normal strain. Now that I have told you what is stress strain diagram, how the situation changes somewhat when it comes to a bar with a cross-sectional area whose cross-sectional area changes over the length. So unlike in the previous situation, the bar shown over here has a cross-section that keeps changing as you move away from x equal to 0. In such a situation, I will not be able to define epsilon to be equal to delta by L, because my strain is a quantity just like stress that can be defined at each point, and defining strain like this, delta by L, is only correct if the bar has a uniform cross-sectional area. If the bar has a variable cross-sectional area, something which is shown in this figure, then what we have to do is we have to bring in the concept of strain at a point. And this strain at a point can be defined by focusing your attention on a segment of initial length delta x before the loading is applied, and by looking at what is this segment delta x going to change to once you apply the load P. So let us say the change in the length is delta del, and I know that its original length is delta x. So for a bar with a varying cross section, I define epsilon at every point as limit delta x tending to 0, the change in length of a small cell element divided by the original length of the small element. And this gives you the expression of strain in terms of the small quantity delta and dx. Now, if you look into the, yeah, go ahead.
Sir, what does strain at a point mean physically? Like,
so strain at a point implies that if you zoom in, if you keep zooming in, see, we are dealing with a continuum. We are not dealing with an object which has gaps in between. No matter how much we zoom in, there is some point that point is going to be occupied by some kind of material, which is with which you have made the bar. So strain at a point over here implies, the normal strain at a point over here will imply what is the small change in deformation of this small zoomed in area that you are looking at. That is the direct physical interpretation.
Okay, so it is not actually a point, but it's basically
no, in continuum mechanics, we define a point. Well, it's a very interesting concept. It's a point, but no matter how much we zoom in, we will still find a material point with some kind of material over there. So even if I have an object like this, I zoom into this region, this small region, I will see that this region occupies some specific domain within my space. Okay, so I hope I am being clear about it.
Yes, sir. Got it.
Yes, sir. Yes, sir.
So the strain, if you look into the description or definition of strain, it is delta by L. Now you can see that delta has units of meter and L also has a unit of meter. So epsilon as a quantity is dimensionless. So keep this thing in mind as we move on. Okay. Now I have told you what stress strain diagrams are. So how do we create such stress and strain diagrams? In order to create these stress strain diagrams, we take help of an equipment known as universal testing machine. And this equipment you can come and see here in our civil engineering lab of IIT Kharagpur. So when you come to the campus, you just drop by our lab. I'll show you. What we do over here is that we take a specimen, we fix this specimen in between these two blocks, and we pull this bottom block downwards. So as I pull the specimen by moving the bottom block downwards, you can think of it as you are applying some force downwards at the bottom end of the specimen. So a typical specimen is indicated over here on the left hand side. So the specimen has an upper grip and a lower grip, and between the two grips you have a cylindrical region which is our area of interest. This is a perfectly cylindrical region before any kind of a deformation. As a result, the cross-sectional area of this cylindrical region is going to be circular. So imagine that you have fixed the top part over here and you have fixed the bottom part over here. And you are pulling the bottom part of the machine of this UTM downwards. So what are you doing? You are applying a force in the downwards direction at the bottom grip, and you are therefore equally applying a force from the top grip as well, because you know that there is no net translation. So since you know the applied force, you can compute sigma n as P by whatever is the cross-sectional area over here for this cylinder. Now, this measurement of P is typically given, it is a computer controlled equipment. So the measurement of P you can typically obtain by means of that computing equipment itself directly. But how do you calculate strain? In order to calculate strain, we take help of what are known as gauge points. So you see over here, two specific points are marked on my specimen and they are called gauge points. And before I begin the experiment, I measure the distance between these two gauge points, and this distance is known as the gauge length or initial gauge length. Now, once I start applying the force, the length L changes. L is going to increase. So let L become L dash, so that my delta L is equal to L dash minus L, right? From this idea, I can compute the normal strain as delta L by L. So from this experiment, I can obtain stress by calculating the area through one of the measuring equipments. Similarly, if I know the initial gauge length through my initial measurement, in between two successive increase of load P, I am going to measure the new gauge length from which I calculate delta L, and from this I can compute the value of epsilon. Now if I simply need to plot on the y-axis sigma n and on the x-axis epsilon n, and since I have the forces at different points, therefore I have stresses at different points. Since I have delta L at different at the corresponding value of the forces, I will have strain also at the corresponding value of the stresses. So I simply am going to join them with curves in order to obtain the stress strain diagram. So this stress strain diagram is very interesting and is very useful. Now the stress strain diagram differs between two materials. On the left hand side, you see a material which is made up of a low carbon steel, and on the right hand side, you see a material which is made up of aluminium alloy. So you see, even for metals, the stress strain diagram of two material is going to be significantly different. But there are some features which we can extract commonly if the nature of the material is similar. That I will come in a short while. So what you can extract from these two figures is that at initial stages, sigma is linearly related with epsilon. That is, sigma n is directly proportional to epsilon. And this proportionality holds true until you hit stress, which is known as yield stress. After you hit yield stress, there is a small region where yielding occurs, where a small increase in force is going to cause a relatively large increase in the strain, as you can see in this region. Beyond that, you are going to observe what is known as the strain hardening region. In strain hardening region, also something similar happens, that there is a small increase in force, but the corresponding increase in strain is again going to be significantly larger. Once you hit the peak of this strain hardening region, that part is known as the ultimate stress. This is the maximum stress that the member can withstand. If you keep increasing the load further, what would happen is there would be necking, which is occurring, that we will see in the next slide. Necking will occur within the specimen and eventually it will break off. Similar feature can also be observed in an aluminium alloy, but not in as beautiful details as we observe in the low carbon steel. In aluminium alloy, we have initially sigma is proportional to epsilon, we have a sigma y, we have ultimate stress, but the clear-cut distinction of a strain hardening region is relatively absent here. We also have the rupture, which is the rupture stress. But remember that even though the stress strain diagram of two materials differ, it does not necessarily mean that the stress strain diagram of the same material will always remain the same. If you change your temperature in which you are performing this experiment, or if you change the medium in which you are performing this experiment, or if you change the rate at which you are applying the external force P on the specimen, your stress strain diagram itself may change. So keep that in mind. So,
excuse me, sir.
Yeah.
Sir, during the necking part, necking region, what happens is that the area decreases in that region. It becomes more smaller area. So if the area decreases, then the stress must increase because its stress is in. I mean, the force upon area. So the stress must increase. But we find that the stress is decreasing, for which the strain is increasing in the necking region. Sir, I couldn't understand that part.
Okay, this is a very good question. So what we are plotting over here is known as engineering stress. So the concept of engineering stress is that I take, in this case, sigma n, and this is equal to P by A naught, where A naught is the initial area. This initial area does not change. This initial area remains fixed. Okay. What you are talking about is known as true stress. So the way true stress is defined is P divided by A, where A is the instantaneous area of the cross section that after you have just performed the experiment. Okay. So what we are plotting in this case, or in most of the true stress strain, most of the stress strain diagram, we are plotting it as engineering stress. On the other hand, if you plot true stress versus true strain diagram, this is never going to decrease even beyond ultimate stress. It goes on increasing and eventually it will break off. So there is no decrease which you will observe in a true stress versus true strain diagram. I hope I am being clear to you.
Excuse me, sir.
Yeah, go ahead.
So then what leads to the decrease in the stress? The force and area.
Why doesn't it remain constant, sir? It decreases.
Okay.
I mean,
so
after ultimate it decreases.
You have a very valid question. So typically, in order for you to explain this, what I said was that the force is applied. Typically, these machines are what are known as the displacement controlled machines. So we do not apply force directly. What we do is, can you see these the pitches, the screw threads, kind of similar to screw threads, right?
Yes,
So
sir.
basically this machine, this end, and there is one at this end, it tries to move downwards. So we are not applying force directly. In these machines we apply displacement. Okay, we are moving this end downwards. Okay, force is being calculated through some other hydraulic jack means. Understood. So in the region where we have this stress, relatively small increase of force gives a large increase of displacement. That simply occurs because the displacement increases much faster than what is happening to the force which is occurring within the specimen itself. So how the machine calculates the force is something of more technicality. If time permits, I will describe, but I don't think the time will permit today. So what these machines do is they apply displacement, because you can see, I hope you are able to appreciate it. I am going, this end is moving downwards and this end is also moving downwards. So basically we are applying displacements, not the force directly. Is it clear? Now, is it clear to the person who asked the question?
Yes, sir.
Yes, sir. Yes, sir. It's clear.
Okay,
Thank you,
okay.
sir.
Hello, sir.
Go ahead.
As although we take constant area in engineering state, but we are also gradually increasing the force P,
Uh-huh.
then stress should be increased, sir.
I'm sorry, I cannot understand. We take a constant area, then what?
And we are gradually increasing force P.
Uh-huh.
Then stress should be increased, sir,
Stress
because
increase.
stress is P by A.
Yes, stress is increasing.
Sir,
So you
in
see
this
the stress
region,
is
sir,
increased.
in the necking region.
In the necking region, this is what I was just trying to explain, that we do not apply force directly. We apply displacement. Okay. And the force is being calculated by the machine itself through some principle of hydraulics, which if time permits, I will tell you. Okay, so force is being computed by the machine. Force is not being applied directly. Displacement is being applied directly. Keep that in mind. Force is computed indirectly. Understood?
Okay.
Oh.
Sir, also for a single force, we are getting two strain. How is that possible?
There is, how are you getting for single force two strain?
From graph, sir, it is bending now at some
Which
point.
part? From this part you are talking?
Sir,
Yes, sir.
sigma y, at sigma y it has been bent.
Oh, at sigma y. Okay. How is it possible? So what happens is, well, I will have to go at the atomic scale in order to explain what happens here. So what really happens is, you see, there is a rearrangement of atomic lattices. So have you come across the term simple cubic lattice?
Yes, sir.
Yes, sir. Yes, sir.
FCC lattice, those things you have come across, right? So when
Yes,
you
sir.
imagine that I have a cube, I'm just trying to explain it in a very simple manner so that you follow. I have atoms which are lying at the each corner of this cube. Okay. And I am applying some force here and I am applying some force here. What is going to happen? The distance between any two atoms is going to increase, right? In other words, the force is a or the displacement or the strain is the manifestation of whatever is the increase in the atomic distance between the two atoms. But if you keep increasing it, then the increase in this atomic spacing is not always going to be in the axial direction. They may come and they may move in a very weird manner, and they may move at 45 degrees to each other. These atoms try to reach in a minimum energy configuration, minimum potential energy configuration. And this is why there are what are known as slip planes. So basically, if you can imagine, there is a cube and I am cutting the diagonal of the cube, diagonal plane of the cube. What would happen is, imagine when I'm gluing the two parts together and I am applying the force. If the force is small, then both of them are going to actually extend, right? But if the two forces are too large, then they are going to slip with respect to each other. Okay, this is what is happening at this location. New slip planes are being created here. These new slip planes cause a rearrangement of atomic position, and therefore all kinds of forces start to in the engineering stress strain diagram you observe a dip. Okay,
Sir, so
I'm
the
not sure whether this
stress,
will be very clear to you because this is a bit advanced concept, but bear with me for the moment. Anyway,
excuse me,
any other
sir.
question? Yeah, go ahead.
So the stress created is actually due to increase in the potential energy of the configuration of atoms.
Correct. But we are not going at the atomic level. That is significantly more advanced for you right now. I personally work at the atomic level, so I know a little bit. So from that side, I'm saying that the increase in stress is occurring because your atoms are basically trying to come up to a new equilibrium potential energy minimum configuration under the application of the forces. That's all you should take the message from this discussion that we have had so far. Anyway, I will not take any more questions because I will not be able to complete this part. If time permits, we will come back to this. Okay. So
Thank you,
now,
sir.
we see that based on the stress strain diagram, you can characterize materials into two parts. One is ductile material and another is brittle material. The typical example of a ductile material is steel, which we saw, aluminium, which we saw, and typical example of brittle material is glass and chalk. So the basic physical difference between a brittle and a ductile material is that in a brittle material, the fracture, the rupture occurs all of a sudden without significant warning to us. So you can imagine, you take a glass, you just hit it with a hammer, it suddenly breaks, right? So there is no warning. You will not find large amount of deformation before breakage or rupture occurs. On the other hand, in brittle materials, because of the presence of strain hardening, because of the presence of necking, you would observe ample amount of warning before rupture or breakage occurs. Okay, so typically what happens is whenever there is a necking, as one of you correctly pointed out, there is a decrease in the cross section, as you can see here. And the failure would occur with a large sound. I mean, when this specimen will fail, you will have a very large sound as if you are bursting crackers during Diwali. Even sometimes sound is even larger than that. And you would observe the failure surface to be something like this. There is a cup and cone failure. Something of this kind of a failure surface you would observe. That here the cross section is large, here the cross section is going to be smaller. Now, on the other hand, if you have a brittle material, the failure would be completely flat. There would not be any necking, there would not be any change in the cross-sectional area. You can see from this specimen that there is no change in cross-sectional area whatsoever. So this is the basic difference between a brittle and a ductile material. Okay, keep that in mind. Now, this brings us to some very interesting concepts. So the stress strain diagram, which we just saw, we observed that the initial part of the stress strain diagram is linear. That is, sigma is directly proportional to epsilon. Okay, so I can say that until the linear regime, I will write sigma to be equal to E times epsilon. And this quantity E, that is the proportional constant E, is all known as the elastic modulus. It is also known as the modulus of elasticity and also as the Young's modulus. So if someone is asking you, do you know elastic modulus? You should say yes. If someone is asking you, do you know modulus of elasticity? You should say yes. And the same thing holds true for Young's modulus as well. Now, if you look at the equation itself, we have just discussed that epsilon is dimensionless. So E has a dimension of stresses. That is E in SI units, it is Newton per mm square, that is Pascals. But typically, the values of E that we encounter in our real life for materials such as steel is very large. It is something of the kind 200 GPa or 210 GPa. For aluminium, it is something like 70 GPa or 75 GPa, something of that magnitude. So you can see that it is very large. 1 GPa is what? 10 to the power 9, of the range of 10 to the power 9. So keep these things in mind. Now that I have computed epsilon and I have, let's say I have the knowledge of E from my previous experiments, can I now relate the deflection of the bar which I've studied initially? So all of these quantities are related. So I have shown you the relation sigma is equal to E epsilon, but sigma for a bar with a constant cross-sectional area initially is going to be equal to P by A, and this is going to be equal to E times delta by L if the elongation of this bar is delta. Therefore, you end up with one of the most profound relationship which you will encounter in engineering mechanics, where the deflection delta is related to not just the applied force and length, but it is also related to the elastic modulus and the area, delta equal to PL over AE. So this expression is very useful in different problems that we will solve later on. For a member with a varying cross section, this idea can directly be extended because we have a situation where the cross sectional area of the member is constantly changing. We have to work with, if I am asked to find out the total deflection at the end, at the free end, it is now no longer going to be equal to del PL over AE, but it's because you cannot define a single unified cross sectional area over here. So what we have to do is we have to take, just like what we did in the previous case, the way we used the definition of strain, the same information needs to go in to calculate the deflection delta. Okay. Let us look into one of the problems. Over here you see a bar with two different cross-sectional area, and this bar is subjected to three concentrated forces at B, at C, and at D. I am asked to find out the deformation of the steel rod. In other words, I am asked to find out by how much amount the joint, the free end at D is going to move. So, you see this bar has a varying cross section. Not only that, for this part which has a constant cross section, for the part ABC, I am having not a uniform axial force. So whatever expression that we discussed, delta equal to PL over AE, this expression delta equal to PL over AE, this is going to hold true across a cross section only if the length is, only if the force P remains uniform, the P remains the same across the cross section and the area of the cross section does not change. But over here you see, from your free body diagram, you would see that the P at this cross section is different. P as the cross section between B and C is going to be different from the P at the cross section A and B, and the P at the cross section C and D is going to be different from the rest of the two. So in such a situation, how do I compute the deformation? If you see, if I focus my attention towards the total deformation, this delta is going to be equal to the relative displacement of D with respect to C plus the relative displacement of C with respect to B plus the relative displacement of B with respect to A. Right? This is the total deflection of D. Now, how do you compute this quantity, relative displacement of D with respect to C? In order to do that, we find out what is the force that is going to occur in the cross section between C and D. So the axial force which is going to occur in this cross section can be found out easily from the free body diagram. So once you find out the axial force, then your delta D given C will be equal to P3 L3 over A3E, where L3 is the length 16 inches. So we have assumed that in this case, since we have not assumed, since the force P3 remains the same across the cross section C and D, we can write this equation in this manner in order to obtain the relative displacement of D with respect to C. Similarly, we can write the relative displacement of C with respect to B and B with respect to A to compute the total deflection delta. Okay. Because of the shortage of time, I will not be able to go through the problem number 2 and the problem number 3. If time permits, we will come back to this. Okay.
Excuse me, sir.
Yeah.
Sir, I had a conceptual doubt that when we calculate the strain, the body is subject to two equal and opposite forces. So the body is extending from both the sides. So then in question 2, when we are calculating the strain, means the change in length, we are considering only the B part. So, and we are taking that as the change in length. Shouldn't it not be the change in length by 2?
This end A is a hinged end, right? We know that the property of a hinge is such that it does not show any deflection. So end A is not going. So imagine, think of it from the perspective that you have a rubber band, you fix the rubber band onto a screw on the wall and you are pulling from the other end, right? The force balance is still there, but the end at which you have connected the rubber band to, is that moving? That is not moving. So you are getting the deflection only at the end where you are pulling it, right? That is why we are not going to consider the deflection at this point. That is because this end cannot move at all in the vertical direction.
Yes, sir.
Understood?
Got it. Yes, sir.
Hello, sir.
Yeah, go ahead.
Sir, if any rod deforms from both sides, then we have to take total deformation for calculating strain.
Correct. If a beam deforms from both the ends, you have to take the net change in length divided by the total length, initial total length.
Okay, sir. Thank you.
Okay. So let's move on. See, I have only 18 minutes and I have a lot of things to cover. So let's move on to another interesting concept, which also you can observe very easily by taking a rubber band and pulling it up. So what happens when you pull the rubber band to a large amount? You would see that the rubber band extends along the axial direction, but in the other two directions, it is going to show some amount of shortening, right? So this concept which you observe in rubber band can easily be extended to any general material. So consider over here a member, and that member be subjected to a force along the x direction only. Therefore, I know that sigma x is going to be P by A. Since there is no force along the y direction and the z direction, I will have sigma y to be 0 and sigma z to be equal to 0. If I rewrite my Hooke's law, I can see that epsilon x is equal to sigma x by E. Right? But as I just told you, in a rubber band, you would observe that there is going to be a shrinkage in the other dimensions. In a similar way, when you pull this bar with the force P, there is going to be a shrinkage along the Z direction. There is going to be a shrinkage along the Y direction. So in other words, there is going to be strain. That is, epsilon Y is not equal to 0 and epsilon Z is also not equal to 0. So this is a situation where you are having strains in absence of the stresses. So even though if sigma y is 0, you still have a non-zero value of epsilon y. Now, how do I characterize? What is the value of this epsilon y that can be calculated? In order to do that, I introduce a concept known as the Poisson's ratio, which is denoted by the Greek letter nu, usually, or it sometimes is also denoted by mu, but we prefer using nu. So this quantity Poisson's ratio is defined as the lateral, the strain along the lateral direction, that is the compression along the one of the direction divided by the axial or the longitudinal strain, and this is equal to the lateral strain along the other direction and the longitudinal and the axial or the axial strain. So using this, I can write epsilon y to be equal to minus nu epsilon x and epsilon z to be equal to minus nu epsilon x. Therefore, this becomes equal to epsilon y becomes equal to minus nu sigma x by E, and epsilon z becomes equal to minus nu sigma x by E as well. Okay, so this is what happens when you have a situation where the force is going to act only along one of the directions. But what happens if the force acts along, that is if sigma y and sigma z are also not equal to 0? In that case, your entire stress strain relationship is going to get modified a little. Our initial stress strain case in absence of sigma y and sigma z was something of this kind. Epsilon y is equal to minus nu sigma x by E, and epsilon z is equal to minus nu sigma x by E. So this occurs when there is only sigma x and there is no sigma y and sigma z. Now when I add the effect of sigma y and I use the principle of superposition, because everything in my problem is linear. Remember, we are only focusing upon the linear region of the stress strain curve. We are not going into the non-linear region. So I can superpose the quantities. So if I now add the effect of sigma y, just by looking at this equation, I can see that epsilon y is going to be equal to sigma y by E, and epsilon x is now going to be equal to minus sigma y by E. Epsilon z will have an additional term minus nu sigma y by E. And if sigma z is also not equal to 0 now, you would have sigma z by E here, you would have minus nu sigma z by E here, and you would have minus nu sigma z by E also here. These sets of equations are known as generalized Hooke's law. So I have now generalized Hooke's law from one dimension to all the 3 dimensions. Okay?
Excuse me, sir.
Yeah, go ahead.
Sir, I had a small doubt here that this Poisson ratio is defined as the negative of the ratio of strain along y divided by strain along x. But Poisson's ratio is a positive number, and the strain is also, I mean, the what is absolute value of the total deformation. So why is the negative sign coming here?
Okay, so when you have a compressive strain, you have the strain to be negative. Strain, how do we define strain? Strain is defined as delta L by L, right? This is how we define strain, isn't it? So how do
Okay,
you?
sir, I got it. I got it. Yes,
Okay.
understood.
Again, I don't have time to go through the problems. I'm really sorry. I only have 12 minutes, so I have a lot of things to finish. So bear with me. If you have more questions, you can definitely write to me, or you can get them clarified in the tutorial class tomorrow with your respective section teacher. So consider over here now a cube of unit dimensions. This cube has initially, before loading, a dimension of 1, 1 and 1. To it, let me add sigma x, sigma y and sigma z. Under such a scenario, we have observed that I am going to have epsilon x, epsilon y and epsilon z. And we have also shown from the generalized Hooke's law what is going to be epsilon x, epsilon y and epsilon z. So if the initial volume of this is equal to V naught, I can compute the new volume V nu, let's call it V nu, as 1 plus epsilon x, 1 plus epsilon y, 1 plus epsilon z. Right? If I neglect the higher order terms, that is the quantities which are squared or cubed in the strain, because strain is a very small quantity, I will end up with an expression epsilon x plus epsilon y plus epsilon z. So you see, what is the change in volume going to be? Change in volume is V new minus V old. In this case, this takes the value of epsilon x plus epsilon y plus epsilon z. And if I divide this with V0, which in this case is 1, I end up with a quantity which is known as volumetric strain. So just like we had the normal strain where we took delta L by L, the volumetric strain talks about change in volume with respect to the initial volume. Okay, so you see, volumetric strain is also known as dilation. Both of them are equal. So you
Excuse me,
see,
sir.
yeah.
Sir, is the dilation equal to epsilon x plus epsilon y plus epsilon z applicable for only cubes and cuboids?
No, it is applicable for all kind of body.
Oh,
The reason why we are doing this is for the sake of
thank you, sir.
simplicity. Okay. So we have epsilon x plus epsilon y plus epsilon z, which defines my volumetric strain. Now, if I substitute from our generalized Hooke's law the value of epsilon x, epsilon y, and epsilon z, which is the generalized Hooke's law, and I add all of them together, I end up with a situation in which you can express the volumetric strain in terms of the stresses. Okay. So the volumetric strain can also be expressed in terms of the stresses, which is sigma x plus sigma y plus sigma z. Now, imagine you are immersing a solid within deep sea. Sigma x is going to be equal to sigma y is going to be equal to sigma z, and all of them three will be equal to minus p, the water pressure. Why minus p? Because our positive sense of sigma x is tension, that is normal should act, it should try to elongate my system. On the other hand, the pressure within the seawater tries to compress the body. Therefore, each of these component is equal to minus p. And if I substitute this information that sigma x equal to sigma y equal to sigma z is equal to minus p in this expression, I end up with a very interesting thing. I end up with a quantity where on one side you have pressure, which is a stress-like quantity, and on the other side I have dilation, which is a strain-like quantity. So you can just imagine the more amount of pressure I am applying, the more change in volume I will obtain. And that constant of proportionality is K, and it is known as the bulk modulus. The definition of bulk modulus is given over here, and it is equal to E by 3 into 1 minus 2 nu. And this defines the upper limit of Poisson's ratio. Because if nu becomes equal to half, you would have a situation where K is equal to infinity. That is, the body is not going to compress no matter how much of compressive pressure that you are applying. It is not going to show a reduction in volume. On the other hand, if nu is greater than half, the bulk modulus becomes negative, and what it would imply is that if you are trying to compress the body, if you are applying compressive pressure on the body is increasing in the volume. That is again very unphysical situation. So nu equal to half defines the upper limit of Poisson's ratio. This brings us to another interesting concept called shear strain. So far, we have only looked at the following cases where sigma x was only acting, and we talked about this as axial stresses, where only the normal stresses are acting. There we talked about sigma x, sigma y, and sigma z. But in the most general situation, you have the shear stresses tau xy, tau xz, and tau yz also acting on a general element. This is known as the generalized state of stress, where you have all the three components of normal stresses and all the three components of shear stresses also in the picture. Now, the corresponding, just like you have normal strains which correspond to normal stresses, we have shear strains which correspond to shear stresses. Now, the simplest way of visualizing what a shear strain is to take a cube and apply the stresses tau xy and tau yx as indicated in the figure. In such a situation, when you have tau xy and tau yx acting on this cube, the initial angle of the faces, which were 90 degree, no longer remains at 90 degree. They are going to be equal to 90 plus some angle theta and 90 minus some angle theta. So the angle between the face has changed, and this changed value of the angle that is delta theta, which in this, or not delta theta, that the change in angle, which in this case is gamma xy, is what is known as the shear strain. Understood? So just like what we have, just like how we have normal strains or uniaxial strains or axial strains proportional to axial stresses, in a similar way, the linear relationship between the shear strains and the shear stresses also hold true. And I have shear strains are directly proportional to the shear stresses, and the constant of proportionality is 1 by g, where g is known as the shear modulus, and sometimes it is also known as the modulus of rigidity. So know these terms, remember these terms. I do not have time to go through the relationship between E and G. So I have only 4 minutes and I want to cover up the indeterminate part. So if you have any questions, just write to me. I'll try to explain them to you. Otherwise, you can ask your sections tutorial teacher, whoever will take your section or your section. Okay, I'll move over to the indeterminate part now. So consider a problem which is, just hold on a second, let me maximize it. Yeah. So consider a problem which is indicated here in this figure as problem number 1. So over here you have a bar which is being kept in between two ends which are hinged. The line of action of this hinge, these two hinges pass basically a line, and in between this bar I have a some point C where I am applying a force of P. Let's say I draw the free body diagram of this case, and the free body diagram suggests that I have RA which is acting and I have RB which is also acting, and I want to find out RA and I want to find out RB. Okay, so how do I go about it? One thing is that which you will appreciate is I can write the equations of equilibrium, RA plus RB equal to P. But from our equilibrium, I cannot use any other equations that you have studied so far. That is because I cannot balance the force in a direction which is perpendicular to RA or RB. I cannot write the equation of moment because moment equilibrium is already satisfied. So how do I go about computing RA or RB? I take the help of my knowledge of deflection, and I take the help that there is going to be no net displacement of this bar AB. That is because since this bar AB is connected to two hinges at A and B, it cannot really move, right? It cannot really show any kind of a displacement. Joint B cannot show any really displacement with respect to joint A. In other words, the net deflection of joint B is going to be equal to 0. With this information, I start taking sections, one section here and one section here. Why am I taking two sections? Because I know that the net displacement of the joint B is going to be equal to 0. I calculate the displacement of joint B to be equal to delta B given C, that is displacement of B with respect to C, plus displacement of C with respect to A. Why have I taken two sections here? Because my free body diagram suggests that in between AC, the force, the axial force is going to remain constant. If I draw the free body diagram, I see that the force, the axial force is going to be P1, which is equal to RA throughout. In a similar way, if I take a cross section between BC, I see that my axial force is going to remain P2 throughout the section between B and C. And therefore, I can make use of the expression which we had initially developed, delta equal to PL over AE. So with this information, if I now calculate delta B given C, where delta B given C I can calculate as P1 L1 by AE. In a similar way, if I calculate delta C given A, that is equal to P2 L2 by AE, the sum of these two quantities must equal to 0. and that is known as the compatibility condition. Why the sum has to be equal to 0? I once again repeat, the sum has to be equal to 0 because the net deflection of joint B is with respect to joint A is equal to 0 because both the joints cannot move in the vertical direction as they are hinged. Right? So I substitute the value of P1 and P2 from the free body diagram. I have calculated P1 to be equal to RA and P2 to be equal to minus RB. And if I substitute them here in this equation, or rather in this equation, I can see that I end up with another set of linear equation in terms of RA and RB. So now I have two equations, RA plus RB equals P and RAL1 minus RBL2 equals 0. From these two equations, you can calculate RA and RB separately. Okay. So I hope I have been able to clarify or discuss the most important parts. I suggest that you go through the relationship between E and G, which was the last topic of the previous PDF that I was showing. I could not show it because of shortage of time, and unfortunately I cannot again also take any more questions right now from you because I have another class to go to, the next sections. So bear with me. If you have more questions, just write to me or you discuss with your section teacher. Either way, whichever way you are feeling more comfortable about. Okay, I'll stop here. Thank you for patiently listening to me. Thank you. I'll stop my discussion here. I'll end the class here. Okay.
Thank you, sir.
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 Thank you.